All right, I wanted to talk real quick about homework one and maybe give a little bit of hints. I think it's a homework that, I think a lot of you guys may just kind of dive right into it and start putting a lot of effort into the math. But if you step back and kind of think about what's the overall concept that I'm trying to get at in the homework, it might make it a little bit easier than it initially seems. So to do this, I mean, the number one thing I'm trying to get at in the first homework is really from problem three and beyond, really. What I'm trying to get at is the concepts that we talked about in the first two lectures. And those concepts, I said, are sort of the guiding principles that we use overall in control systems, which is basically to say, in a control system, what I want is good command following. Okay. I want a good command following. I want good disturbance rejection. I want good noise rejection. All right. I want good, or maybe I should say that better as low, not slow, low sensitivity to parameter fluctuations. And then five, I want stability. Okay. Now, we did all of this in the context of our basic control system model, which we said I could turn into this guy. Okay. When we analyzed this guy in class, we said I've got a reference input, a disturbance input, and a noise input. And I said that ultimately that C of S could be written as L over 1 plus L times R plus, as I've written it here, 1 over 1 plus L times D minus L over 1 plus L times N. Okay, so we went through and we analyzed this in the context of these things, right? So what we said was, if I want good command following, that means that in steady state, so in steady state, I want C to approach R, all right, if there's no disturbance and no noise. All right, to get there, for that to happen, I guess I'll say it this way. I want C and R to be approximately the same, which we said meant that L needed to be big. Okay, for good disturbance rejection, we said in steady state, I want L to be much, much greater than 1 again. Okay, if L is much, much greater than 1, this term goes away. For good noise rejection, which I don't touch in this homework, so I'm not gonna talk about that one. All right, because it's not in the homework. Neither is stability, so I'm gonna skip these two. The other one that I talk about here in the um, assignment is this low sensitivity to parameter fluctuations. For that guy, what we said is that in steady state, again, I want the magnitude of L to be much, much greater than 1. Okay? So for all of this, when I say low sensitivity to parameter fluctuations, L is much, much greater than 1, what that means is if the specific values, the time constants and things in this L of S are kind of changing over time, as long as the magnitude of L is much, much greater than 1 in steady state, then this guy, those fluctuations don't matter, okay? So we're testing this here. Basically what it comes down to for this guy, and this guy, for all three of those things, those are all steady state things, and they basically tell us that in steady state, we want the magnitude of L to be large, okay? In other words, the open loop gain around this loop to be large, okay? So what this homework is all about is, what is steady state, okay? That's kind of the question. What is steady state? How do I deal with steady state? Steady state in general, what that means is that all of our derivative terms have gone to zero, okay? And so the system has stopped changing, okay? So in that context, that means that if R is a step input, that means that C has settled out to a steady value, okay? So steady state, oftentimes, if I think of, okay, think of a system like an RC circuit. If I put a step into an RC circuit, the output voltage will look like that, okay? So what it means is that this is the transient period, and somewhere out here is steady state. Basically, steady state also typically tends to mean as t goes to infinity, right? So if I wait a long time, so in other words, a long time after the inputs are applied. That's what t equal to infinity is. As t approaches infinity, that's a long time after our inputs are applied. So all of the change in state associated with charging this capacitor or charging the inductors or whatever, all of that variation has stopped, okay? And so I've reached a steady condition. So as t goes to infinity, that says, okay, well, as basically I get to a condition where everything is constant, that time going to infinity is very much what we sometimes consider DC, right? In other words, if everything's become constant, I'm in a DC scenario, meaning that my frequency is basically zero, right? As t goes to infinity, right, I get to a situation where there's no further fluctuation in this system. And it's basically like the frequency here has become equal to zero. So to analyze this stuff, right, if I want to look at steady state conditions, I either have two choices. I can look at my differential equations, or I can map my differential equations over into what we call the frequency domain, right, and use a Laplace transform. So if I have a Laplace transform, right, let's say I have x of t is some signal. It has a Laplace transform x of s. If I want to know the steady state value, so I'll call it x steady state, all right, I'll say that x steady state is the limit as t goes to infinity of x of t, okay? I want to know what that steady state value is. Well, there's a theorem that you can look up in any signals and systems book, and you guys saw it. It's called the final value theorem for Laplace transforms. Okay, we will use it a lot. All right, it allows us to look at steady state using transfer functions. Okay, final value theorem for Laplace transforms. Look it up in any signals book. You should have seen it at some point. Basically, in words, what it's saying is, if I'm looking at a signal, let's say this guy was x of t. If I want to know, and let's say this x of t, let's say the final value of this guy is 5, okay? Well, so in this particular case, what it says is, as t goes to infinity on this x of t, this guy better be 5, okay? If I want to analyze that and know that same value from just looking at the Laplace transform, I plug in s equal to 0, right? So t going to infinity meaning that, okay, everything steadies out and I'm long after the transient, is like looking at the DC condition in a transfer function, okay? It's like looking at, remember, S equals j omega. So when I look at omega equal to 0, it's like I'm looking at t going to infinity, okay? So we use this final value theorem a lot to be able to look at our transfer function, to be able to say from our transfer function, you know, what is it that we have in steady state, right? It allows us to pull the steady state stuff out of the transfer function. So in the homework, you basically have a system that looks like this, okay? And then down here, there's a sensor, okay? I call this C of S. Now the plant is given, and this is given. So what you should see is that C over R equals GC GP over 1 plus GC GP H, like that, okay? This is what we have. Now, like I said, G sub P, the plant, and H are given to us, all right? In this system, L of S is G sub C, G sub P, and H, all right? For my basic stuff that I cared about, so my good command following, my disturbance rejection, and my low parameter sensitivity, I wanted L of S to be much, much greater than 1, okay, for all of those conditions. Well, in this case, and I said in steady state. So what that means is as S goes to 0. So in this case, since GP and H are given, the only thing I have control over is G sub C. This guy is our controller. And what I want to have happen is, because I want L of S to be much, much greater than 1 in steady state, what that means is that G sub C of S, I want to be much, much greater than 1, okay? If I want to achieve good command following, so here. So if I want good command following, good disturbance rejection, and low sensitivity to parameter fluctuations, I need to make sure that my G sub C of S is equal to 1. So in the homework, I have you consider two G sub C's. One is KP, one is KP plus KI over S, okay? So what I do is I have you consider these two scenarios, okay? Couple of things, right? If I just look at this, since I said that steady state is basically this whole limit as S goes to 0, well, that tells us some important stuff, right? If I look at this particular controller here, as S goes to infinity, I see that the value of G sub C approaches infinity, okay? That's going to make this large and make sure that I have good command following, good disturbance rejection, and low sensitivity to parameter fluctuations, okay? If you keep this in mind, okay, what you will see is the homework, don't get too lost in all the math, right? Basically what you're going to find is that when you use the KP for the controller, I'm going to say, when I have KP as the controller versus this guy as the controller, when this guy is the controller, G sub C is going to get as large as possible, and I'm going to have perfect command following, perfect disturbance rejection, and perfect sensitivity to parameter fluctuation. If I just have KP, it's not as good, okay? And so basically, we have names for these two guys. This guy is sometimes called a proportional controller. This guy is sometimes called a proportional plus integral, okay? This term right here is the Laplace transform of an integrator. Okay, and so we can build that, you'll see, with a very simple integrator circuit or an integration in code, right? Which we'll talk about how we build that in code. But basically, all we're doing in this homework is looking at the effects of these two controllers using this Laplace final value theorem. And the whole idea of that is basically to say I want to analyze the system in steady state, and I can use this final value theorem to say, well, in steady state, meaning as t goes to infinity, what happens as the frequency goes to 0? All right, that's going to tell me what the system's going to do in steady state. All right, keep that in mind. What you should, there's an answer you should expect to get in the homework. All right, and what you should see is that as this g sub c gets bigger, like when I use this guy, I'm going to get closer to perfect results. So perfect command following, where c is equal to r. Perfect disturbance rejection, where L is gone, or sorry, where the disturbance is perfectly rejected. All right, so that's what you guys need to think through in this homework.